Here is what we are going to build today. It is a text-based car simulation game that runs directly in your terminal, responding to live commands to start and stop an engine, complete with custom error handling. If you have never built an interactive application before, we are going to write this entire engine from scratch in the next 6 minutes. To pull this off, we need to combine 3 core Python mechanics: grabbing live user inputs, trapping those inputs inside a continuous game loop, and using variables to track the current state of our car. Moving from writing static scripts that run once and die to building continuous interactive loops is the leap you need to make to write real-world software. We start our engine by typing while true, followed by a colon. Below that, we indent our code and prompt the user for an input. This establishes our primary game loop. The cause true always evaluates true. This forces the interpreter to endlessly wait for the user to type something over and over. Without a way out, an infinite loop locks up the terminal. We map quit to a break statement as an emergency exit. Next, we use an if, elif, else block. Start and stop trigger print statements, while invalid commands funnel back to the prompt. Let's test this in the terminal. We type start and it starts. We type gibberish and it rejects. Finally, we type quit and the program shuts down cleanly. Designing a program that waits for instructions, processes them, and returns to a ready state is the basic architecture for persistent interactive software. Watch what happens if a user types start in all capital letters. The program throws our default error message because it only recognizes the exact lowercase string coded. We could write endless conditional statements checking for every possible capitalization of start, but that duplicates our logic and clutters the code. This diagram illustrates our fix. By attaching the .lower method directly to our input variable, we convert whatever the user types into lowercase immediately before the program evaluates it. Users also need to know what commands are available. We can build a help menu using triple quotes, formatting a string across multiple lines. Look closely at the code formatting here. Because triple quotes print text exactly as it appears in the editor, we have to pull this specific block of text all the way to the far left margin. If indented to match our loop, those empty spaces will print directly to the terminal. Back in the terminal, typing an uppercase start now works perfectly, and calling help returns a clean, properly aligned menu of commands. Preemptively sanitizing user data ensures that a program remains functional regardless of how the end user formats their input. There is still one logic flaw. I can type start, get the confirmation message, and then type start again. The program blindly tells me the car has started twice in a row. This happens because the application has no memory. It evaluates every command in isolation, completely unaware of what happened on the previous turn. To fix this, we need to track the car's state. We create a Boolean variable called started and set it to false. We place this entirely outside our main loop, so it doesn't get reset every time the user types a new command. Looking at this logic gate, we can see the updated start condition. When the user types start, we first check our Boolean switch. If started is already true, we route them to an error. If it is false, we print the success message and immediately flip that switch to true. We mirror this logic for the stop command. By using the not operator, we verify if the car is currently stopped. If it is, we block the command. If the car is running, we confirm the stop and flip the Boolean switch back to false. Running the game one last time, if we try to start an already running car, the program catches the state and prints our custom error. By defining state outside the loop, we provide the program with the memory it needs to evaluate commands based on what has already happened. Let's run a full, uninterrupted test in the terminal. We call for help, start the engine, hit our custom error by trying to start it again, stop the engine, and safely quit the application. In 6 minutes, we combined an infinite while loop for continuous execution, conditional branches for logic routing, string methods for data sanitization, and a Boolean variable to track system state. Your next step is to expand this code on your own. Try adding a drive command or a new variable that tracks a fuel level that drops every time you execute a move. This structure, this state-managed loop, is the framework you will use whenever a program needs to react differently based on its own history.